Today we have Naveen. It's a pleasure to have you, Naveen, here. He is a postdoctoral fellow with us, and he did his PhD with IIC and RRI to IIC. He worked with Sridhar for his PhD, and then he joined us a year back, 2 years back. You joined here as a PDR, and then he joined here as a PDR, and then joined as a PDF. So he has completed 1 year of his PDF, and he will present his work on observational signature from shear dynamo simulations. All yours, Naveen.
Thank you. Good evening, everyone. Am I audible? Am I audible? Today I talk about the observation signature from the shear dynamo simulation. So this is the work that is carried out with Saranya and then with the collaborator. So observational signature, what I mean by observation signature is that the Faraday rotation and the synchrotron emissions of the polarized light. So generally these quantities are detected routinely in radio observations, and from this one can furnish the information of the magnetic fields that are present in the wide variety of the objects in the astrophysical systems. So our primary interest is in okay, this is a picture of a cosmological simulation. This is a cosmic wave where this is how the universe is at the present epoch. Where it shows the filament structure, and then it shows the junction point between those filament structures, where these are the places of the galaxy clusters, basically, where the junction points of the elements are. So I'll briefly give the overview of galaxy clusters, and then I talked about the shear dynamo simulation that I had done here on the Nova cluster, and then I'll talk about the rotation measure that is going to be calibrated in this, and then I'll brief about the synchrotron emission and how it compares with the observation. Galaxy clusters are actually the largest gravitationally bound objects that are known to us till now. So this is the present day knowledge of the universe. That is, there was an initial density fluctuations, and this density fluctuation, because of the gravitational instability, started growing in time. And when this density fluctuation crossed certain threshold value, they started forming the structures. The structure started forming. First, the galaxies formed, and then the galaxies merged, and then they formed the hierarchical clusters. So this is actually the hierarchical model of the structure formation. So here what we see is the filament structure, and here the bright spot is the galaxy, which is the interest for us today. If you just zoom in the this part, we can see here, for example, I have overlaid the coma cluster radio observation plot here. So where we can see that there is two clusters which are sort of approaching each other. This front indicates the shock front. Okay, this is the radio halo that is encompassing all of the galaxies, and this is sort of approaching each other.
Sorry, the plot is the simulation illustrates TNT.
Yes,
the fully simulation.
Yes, that is a fully simulation. I have just overlaid it on the observation. So these are some of the properties of the galactic clusters. These clusters have the the galaxies on the range from something like 1,000 to 1 lakh, and the radius of this cluster is around 1 to 2 kiloparsecs. The extent of this cluster is something like 4 kiloparsec or so. Sorry, megaparsec. Sorry. So kiloparsec is the galaxy size. So the temperature in this varies from something like 10 power 7 to 10 power 8 Kelvin. So they are quite high temperature compared to what we observe in the galaxies. So central regions are generally cool. The outside regions have a temperature something like 10 power 8. I'll explain in the next slide why that is the case. And this cluster has around 10 to 30 of the gas as compared to the virial mass of the cluster. In this virial mass, even the mass of the halo is considered, the dark matter halo. If we deduct that, then the amount of gas that is present in this cluster is actually equivalent or exceeds the mass that is present in the galaxy, visible light. So the velocities in these are on the average of 100 to 300 per second, and the sound speeds are 1,000 km per second. So this is if we divide this velocity by this, then we get a Mach around like 0.1 to 0.3 around that range. So it is a subsonic system. So this galaxy cluster has a very bright X-ray emissions. Okay, this mainly happens due to the Brimstone radiation, which is happening between the charged particles due to Coulomb interaction. And then there is a diffuse radio emissions, which is observed in this cluster due to the synchrotron radiation. And this diffuse radiation has been observed that it is not part of any galaxies or any part of not part of any galaxies, but it is just whole of the cluster, the radio emission that is there. And because this is synchrotron radiation, and synchrotron radiation happens in the magnetic fields, these relativistic particles going in a spiral path. So one can measure the magnetic field strengths of the order of something like the 1 to 6 microbars clusters. So because the temperatures are higher, the viscosity of the gas goes like root T. So viscosities are generally higher. So they have the Reynolds number which are pretty low, around 300 to 400. Whereas the eta, which is the resistivity, which goes like 1 over the temperature, because of the high temperature, the resistivity is really large. The eta is really small. So because of which the magnetic Reynolds numbers are really huge in this kind of system. So if you look at the Prandtl number, which is the ratio of this nu times eta, which is much larger than one of these systems.
So the magnetic Reynolds number is large, which means that turbulence, magneto turbulence to happen, it is difficult, right?
No. Reynolds numbers. See, if Reynolds numbers are generally, it is believed that when this viscosity is higher, then the turbulence is tough to happen. But people have observed it because this is sort of a compressible gas. There are density variations. Turbulence do sort of set in the system.
Even with magnetic.
See, setting up of the turbulence is independent of the presence of the magnetic field.
Oh.
Just like in water, in any usual system, that you can set up the turbulence without the. So what you're, I think, talking about is the MRI, where
where magnetic viscosity.
That is a different idea.
No, but essentially turbulence is because the medium is highly viscous. There's a shear stress in between various layers.
Yes.
And when the fluid lines break off is smooth, so you have turbulence.
Yeah, that I'll explain it in a
So when you introduce magnetic fields, it introduces magneto-viscosity, which is why you have turbulence and turbulence. And the absence of fields also just depending on the viscosity.
Yeah, that is true. See, in case of, for example, the neutron stars or this accretion disk, so the magnetic fields are really high there. I mean, their magnetic field strengths are much higher than what is the energy present in the magnetic fields is much higher than the what is present in the fluid motion. So because of that, there the magnetic stresses are more important. Here, that is not the case. It is just a microgauss field. I mean, what you are talking about is like Tesla, the field strength of the order of the Tesla.
So here the Reynolds number is small, but the magnetic Reynolds number is still high.
Yes. The fluid Reynolds numbers are generally small because of the high temperature.
So the Prandtl number is also greater than 1.
Yeah,
magnetic Prandtl number.
Yeah. It is actually estimated that it is around 10 power 20, 10 power 29.
Again, the resistivity you are referring to is that Spitzer resistivity.
Yeah, it is the Spitzer resistivity. So now this is the sequence of the galaxy. In a lifetime of the astronomer, we cannot actually observe, the merging activity that is going on. Here it is, the merging of the galaxy clusters at the different phase of and across different objects are, collected together in this image. So what we see here is the X-ray emission that is coming from this region, which is represented by the blue, and the red is actually the radio emission. And on the right, I have shown the different instruments that were involved in taking the X-ray data and the radio data in this clusters. This is the raw resolution from that, and this is sort of a high resolution image. Here we can see that, this is the image where both clusters have merged, and this is the time after 0.6 gigayears after the merger. And one can see carefully, if you look at, there is a density variation in the intensity variation of the X-rays across this. So which sort of indicates that there is a pressure fluctuations in this system, and that sort of indicates that there is a presence of.
Let us clarify something to sound basically, there are different events, right?
They are different clusters. For example, this is Abel 399.
Thank you. Because
It is
I looked at the timeline between Rosat and Shah. That's a really fast moving cluster.
no. This is a different cluster because we can't see them.
I understand. Okay,
So
yeah,
this is
like-
from
Like
the.
I said, it's a trivial.
So there is this X-ray intensity variation that is happening, which sort of indicates the pressure fluctuations that are going on in the system. So that is directly correlated to the presence of the turbulence in the system. So generally, the clusters are broadly divided into two classes. One is called the cool core clusters, and another one is the non-cool core cluster. In the cool core cluster, what happens is, if you look at the X-ray intensity, it has really high peak at the center. And in the non-cool core clusters, the X-ray intensities are not so much high; they sort of spread across. So here in this cluster, what happens when there is a really high X-ray emission? This is generally happening because of the Bremsstrahlung emission. So as the emission is happening, this cluster starts cooling. The gas starts cooling, and when the gas starts cooling, its temperature sort of decreases, and the pressure decreases to support the outside gas. The inside of the gas has to support the annulus of the gas that is outside. Pressure will support it. For that to happen, the gas here starts moving inside, and the rho starts increasing. As the rho starts increasing, the emission still increases further because the emission of Bremsstrahlung is actually stronger power of the number density as compared to the temperature. This sort of leads to the vicious cycle, and because of this cooling flows, actually this gives rise to something called subsonic turbulence in the system. And this vicious cycle sort of gets broken up when the two clusters of starts merging each other. So let's say there's a cluster of mass M1 and M2 when they're approaching each other with certain impact parameter. So at the junction of those impact, one can see that the velocities are directed in opposite direction with different density of the clusters rho1 and rho2. So this is a classical Kelvin-Helmholtz instability that happens in this cluster. That is when there is a fluid which is of different density rho1 and rho2 sitting on top of each other with certain velocity difference across them, then it can leads to the instability, which is called the Kelvin-Helmholtz instability. So because of this instability, there is expected to be a turbulence that gets set up in the system.
Usually it is when the lighter fluid is pushing the heavier, like in supernova debris.
Yeah.
Okay, so will that will be a constraint here, one galaxy cluster should have a higher velocity than the other.
See, there is two parts to this calculation. One, the Kelvin, what he did was he did it in the gravitational field. Okay. Where the lighter fluid is sitting on top of the heavier fluid. So what Helmholtz did was he extended it to the accelerated system because having a gravity or having an acceleration is sort of equivalent. So if you have a denser fluid accelerating towards the the lighter fluid, it sort of also gives rise to the instability. And this kind of a flow gives rise to the shear flows in the systems, in the merging galaxies.
Mean at the one day.
At the junction. So the evolution stage of the mergers are generally lasts for something like 3 to 5 gigayears. And after this phase, like the turbulence sort of decays for another 4 to 5 gigayears. For us, the point phase where the turbulence is sort of considered steady. So we model this velocity field as a linear shear flow, which is varying along the direction x1 linearly, which is pointed in y direction. On top of that, we overlay the turbulent velocity. Yeah.
Does the Kelvin-Helmholtz instability also depend on the shape of the geometry of the two species?
No.
But it does depend on the temperature, right?
No, this is isothermal calculation.
So it depends on just the density.
Density difference and then the velocity difference, that is nothing else.
It will not depend on the two galaxy clusters, like the interface of the two galaxy clusters being spherical or something.
No. So this is like you zoom into the space, where closely. Then this, I mean, this has to be considered the local patch of the galaxy cluster.
Okay.
In a way. So here we model the cluster's large scale motion as a shearing motion, which is in the direction of y, but it is varying along the direction x. On top of this mean motion, we put in the average, the turbulent velocity, whose average is actually 0. So even though our model, even though we are motivated by the galaxy clusters, what we do, the calculations that we do is not just limited to the galaxy cluster alone, because even such kind of shear layers are observed throughout the astrophysical systems. So one such case is the galaxies, where the differential rotation is also can be modeled at a local patch like a linear shear. So what we do is we take this local patch and then incorporate this shear, which is coming due to this differential rotation. And then we try to solve this, both induction equation and the fluid equation simultaneously in a pencil code setup, where we introduce the turbulence in the system through the forcing function. Forcing function is generally which is considered to be a homogeneous isotropic, and it is forced non-helically without introducing any helicity in the system.
So these are just toy clusters, or you take actual values?
Right now we are just trying to see what signatures that these large scale motions can have on the observers. Later it could be extended to
These equations have been normalized, right?
no, they are not dimensionless. They are not.
How you are equating.
No, this is just this is Navier-Stokes equation. I have put in the average velocity in them in both the Navier-Stokes equation and then
the shear ratio, the Young's modulus and the shear.
Yeah.
For the component of the Young's modulus in the shear direction, tangential direction.
So shear is actually the rate of.
Typically, shear is defined as stress over strain. I mean, basically, all of them are stress over strain.
Yeah.
Right. So this, okay, so that's a dimension.
So shear has a dimension of 1 over time, and this
Okay, fine.
like Sx will give you the velocity dimension. So then let's look at the two plots. One is for the zero shear case and the shear case. This is just I'm showing the magnetic field growth, how it happens. People had done this calculation for the no shear case. I'm extending it to the case of a shear, including the shear in the system. So is this 3D or 2D? This is 3D. I mean, this is a box simulation, in all three directions. So here we can see that the magnetic field sort of decays initially because of the diffusion. So that once it latches on its eigenfunction, then it starts growing exponentially. Then it saturates because of the back force of the events on the velocity field. So on the bottom of the panel, I have shown the XY average of the Bx and the By. This we have done the forcing at the half of the box scale. So we can see there are patches in the magnetic field values, positive and negative values, and these patches are sort of sizes having less than the box size. So this sort of indicates that this is a small scale dynamo, which is what is expected in this kind of system.
What is the top panel? You scaling the B. What is the? I can't see that.
Okay, that is B equilibrium. That is
B equipartition.
B equipartition. So that is defined as rho times rho times Q square. Mod of this is energy density. Mod of that is
That's what you are normalizing it. So the other one and the numerator is what?
This is time. Time is normalized with respect to the eddy turnover time.
No. The magnetic field is the magnitude of the magnetic field.
This is the magnitude of the magnetic field with respect to the equipartition.
So what is the starting field strength input?
Starting field strength, just if you look at B, it is 10 power minus 4 or something. 4.
So uniform.
Uniform field. Gaussian random uniform field. Unitless. With unit, I think it will go up to like 10 power minus 4 years. With this unit, let's say in dimensionless unit, it will be something like 10 power minus 3. So in the case of shear, for example, I have run the simulation with the Prandtl number 80 and then with the shear rate 0.07. So this shear rate is chosen because we wanted the energy that is present in the shear is equivalent to the energy that is present in the turbulence. So which is sort of expected in this kind of an instability. So one can see that with the presence of shear, the BRMS actually grows quite fast compared to the no shear case. Okay, and then it saturates to the partition stream. And in the BY component, one can see that there is a large patch, and also the value of the magnetic field is at least some 3 to 4 times higher compared to the BX component. So the magnetic field becomes actually anisotropic. In case when there was no shear, the magnetic field is sort of isotropic. So because of the linear shear, it makes the magnetic field anisotropic, which will have in turn the influence on the observers.
See, the magnetic random number is also different. So the difference is due to the magnetic random number or because of the shear.
No, it is because of both in a way.
Right. But whoever fix the Prandtl number and do the shear.
Yeah, I have done that for the demonstration purpose. Like I'm showing this. Because in see actually really large difference. So with the if I had same Prandtl number, then the difference is very less for this values of shear. So to have the really accentuated difference, I have to increase the shear value, which was unphysical because I wanted the energy that is present in the shear, which is equivalent to the turbulent energy. So in the clusters, anyway, the PMs are really high, and even in the galaxies.
Compared to your input, how much is the saturation value for your magnitude of the magnetic field?
It will grow up to the equipartition strength. So let's say, for example, in the code unit, it is 0.1.
Okay. Given a -4 order,
yeah,
this will go to minus
0.1. 0.1. So how are magnetic fields detected? They are generally detected by the Faraday rotation. So in the magneto-ionic medium, what happens is the normal modes are the left circularly polarization and right circular polarization. So because of the presence of the magnetic field in the system, what happens is this polarizations, which are left circularly polarized and right circularly polarized, travels with a different speed. They experience the different refractive index. And that difference mainly comes because of the presence of this omega c, which is the cyclotron frequency in the system. So any linear polarized light could be, diffused as a combination of the LCP and RCP. So when we do the analysis, what comes out is that the angle of the polarization becomes a function of the density and the magnetic field. And as the light passes through the medium, its plane actually rotates, and the rotation actually is proportional to this quantity. So this is the thing which is general, that the theta is lambda square times Rm. So it is proportional to the light wavelength. So larger the light wavelength, more the rotation that happens. So so low frequencies are better for the RF measurements for this to detect the magnetic field.
If we don't see RCP, when a plane wave will add rotation, then polarized wave.
See, that's what I'm saying. See, this is the LC is the normal modes of this plasma with the magnetic field. So any linearly polarized light can be decomposed into this orthogonal basis. So because they travel with slightly different speed because of this difference, that the plane of the polarization rotates. That is the effect that is seen.
And that is related to the gyro frequency.
Yeah, it is inherently related to the gyro frequency. The similar thing happens even in the, for example, sugar solution that is seen in the laboratory, that when you have a sugar solution, when the linear polarized light passes through it, the plane of polarization rotates. And it is observed that even the sugar molecules sort of arrange in a spiral fashion, in a helical fashion. So the plane of polarization is actually rotating because of this spiral motion of the electrons around the magnetic field. If you don't have this, then both LCP and RCP travel the same speed.
I'm just wondering, do we need to then think of some, like this omega c should be some lesser than the collision frequency? Otherwise, it may not decompose differently.
No. See, here, up till here, there is no assumption. To calculate this formula, so one actually assumes that the omega c is much smaller compared to this omega, and then you make a binomial explanation, and then you get this. So, which is generally the case in this, plasma systems. So on the right, I have shown the rotation measure of the Bell clusters, like many clusters, which is taken from this paper. So has plotted with respect to the impact parameter. Impact parameter meaning the distance from the center of the cluster. So at the center, one can see really the large RM value, which is of the order of something like 150 up to going up to 200 rad per meter square. So in our simulation, what we do is, because this is we are taking a local patch, the average magnetic field is actually 0. So the average RM that we get is 0. So what we look at is the dispersion measure. So we look at the root mean square value of the RM. So which we get by taking the square of this and then taking the root. So this we can show that it is actually proportional to the VRMS value of the magnetic field times the Lx, which is the integral scale of the magnetic field in that particular direction. So one can do a similar exercise for the all three direction, and corresponding integral scales sort of comes out. So if you measure this, we can sort of know both like VRMS and then the integral scales of the magnetic field, the scale of the magnetic field in the systems. So this is for the zero shear case, where I have shown the sigma RM. Here what I have shown is the normalized sigma RM. So I actually use certain particular theoretical model to normalize. So what this model is that there is a VRMS field which is uniformly filling the cube, all the turbulent cells. So this particular model is chosen. This gives the maximum RM value. So with respect to that, this RMs that we get from the simulations are scaled, and it comes out for this zero shear case around 0.4 to 0.5, which means that the dispersion, the rotation measure is sort of 40 to 50% of the theoretical maximum value that is possible. So one can also calculate the magnetic integral scales in the systems. Here I have shown the magnetic integral scale, the scale with respect to the box size. Here, because in the previous slide, I have shown that this goes like the integral scale. And you can clearly see that trend in the simulation, that it follows the trend of the sigma RM. So here I have shown the velocity integral scale. This is the 20% of the size of the box. So this value is actually smaller than this, meaning the integral scale of the magnetic field is smaller than the velocity integral scale. So this is actually the small scale dynamo, because of which the integral scales of the magnetic fields are lesser than the velocity integral scales. So in case of shear for this particular value, so the RM, especially in the y direction, that is in the direction of the shear, actually has a quite large value as compared to the other two directions. That is, this is the x direction and this is the y direction. So it's almost 2 times what we find in the other two directions. So compared to this previous, it is like 40 to 50%, and particularly in the y direction, it is around 60 to 50% value. So a similar trend is also seen in the integral scale of the magnetic fields here, and velocity integral scale sort of remains same compared to the previous case, the no shear case. Only the magnetic integral scales are increasing. That is happening because of the presence of the shear. What I showed in the space-time diagram, there we had observed that there was a bigger patches of the magnetic fields. So this sort of correlates with the presence of the larger scale magnetic field that is coming because of the shear.
They don't have the red one.
For average one, I did not plot it. The red one is the average of this.
Oh,
Average of, because we cannot really decide which direction is the shear in the sky, right? I mean, what we measure is sort of combination of this. If you happen to measure in that direction of shear, then we'll measure probably the larger value, otherwise not. So here the RM is sort of direction dependent. This is not the case for the polarized emission. I'll show it.
Well, you said in the previous case, it's zero shear, the small scale that.
Yeah.
The next case, what kind of dynamo?
This is also small scale dynamo because again you can see that the integral scale of the velocity fields are larger compared to the magnetic integral scales. We wanted it to be because we are forcing the simulation like at the half of the box size. So there is no space for the large scale magnetic field to go. You can see in this cluster when they're merging, the energy injection is happening at the larger scale, starting from the larger scale, instability setting up at the larger scale. Then the energy is sort of cascade smaller scales.
So in this case, this is the processing. Okay, so what about the
What is it meaning? Vorticity of the magnetic field or velocity field that I have not looked at, but it would generally follow the trend of the velocity field itself in the incompressible case. This is weakly compressible case, pencil code, right? So it will sort of follow the trend of the velocity field, because if you look at the Fourier transform, the omega is just a k square times u. Omega is just k times u. So the behavior of the u is sort of imprinted on the omega.
They would expect also the value
Like this. No, this is the magnetic field. This is the velocity field integral scale. So even the vorticity integral scales would be similar, like this. Vorticity of the vorticity of the fluid. So if you just take the naive numbers from this figure and input it here, like density value 10 power minus the magnetic field value, then we can expect that the rotation, the dispersion sort of goes up to like 270 rad per meter square. This is happening because of the shear. This is an ongoing, but still more comparisons that we're going to do later. Now I'll come to the synchrotron emission. The synchrotron emission generally happens when the the electron is going around the magnetic field in a circular fashion. In a non-relativistic limit, the electron emits sort of a dipole radiation. So if electron is really at the relativistic speed, then it emits, because of the beaming effect, the radiation that is emitted is predominantly in the forward direction. This makes the light completely linearly polarized in a way.
Depends on the viewing angle in the non-relativistic.
Huh.
Right?
Yeah.
It depends on where you're looking at.
Yeah.
Non-relativistic means cyclotron.
Yeah, non-relativistic means cyclotron. So relativistic meaning.
No,
like,
you can have synchrotron non-relativistic. It's simply a question of your magnetic field being non-uniform.
Synchrotron means relativistic.
Synchrotron means relativistic.
Sure of that.
Yeah.
Only the variation of what was the variation of the magnetic field dBdx.
No, see, this is just I'm showing one single electron that is going around the magnetic field at certain local time. Just
Yeah, I know that, but your field doesn't have to be constant, right?
Yeah, but see, there are certain scales involved, like the scale of this gyration frequency scale, like gyration radius, is actually much smaller than the magnetic field variation scales.
I know, so you're not talking about, you don't confuse with curvature radiation. That's what you're trying to say. Right? I mean, electron is tied to the magnetic field. If the field is actually curved, then you can have curvature radiation in addition to those variation from the, that's a standard, that's your standard electron tied to a magnetic field. And
yeah, this is what
constant figure. But even along the line of, along the field line, you can have a non-constant component of the magnetic field, right?
Along the.
You have d x y z, dx dy dz.
Yeah.
Right? But you can also have a db dx, db dy, db dz. You have that.
Yeah.
So what would you call the radiation that?
See, generally radiation comes because of the acceleration of the charge. Yeah.
Yeah, we both agree on that. I think what I'm just trying to stress is that if you have a changing magnetic.
There is an additional acceleration that we observe on top of this, which would also result in a sort of an emission.
Result in synchrotron emission.
That I don't know, because see, then it depends on the parallel components of the velocity field. See, this is relativistic. So if the parallel component of the, we have to look at whether the parallel component of the velocity field is really relativistic or not. If it is, then of course that will also give the radiation in the direction of the magnetic field where it is curving. So meaning, let's say if it is curving, then if it is zipping through like this, then it can give rise to also the radiation in that direction also. So this beaming effect is coming because of the simple fact that the total velocity of the photon and the velocity of the electron, which is v here, should not cross the speed of light. So if the electrons are already moving in the u parallel direction, the u parallel is almost equivalent to c, so u perpendicular has to decrease. So because of which there is this beaming effect that happens in the which is a relativistic effect. So in the cyclotron radiation, we have both linearly polarized light and the circularly polarized light. Linear polarization comes in the direction that is perpendicular to the magnetic field, and in the direction parallel to the magnetic field, it emits the circular polarization. Whereas in the synchrotron radiation, the light is predominantly linearly polarized. So one can do the calculation like as it given in Rybicki and Leitman, and they show that the amount of intensity that is emitted in the direction perpendicular to the magnetic field is seven times the energy that is there in the parallel direction. So because of which it will have very high degree of polarization. So this is like I've computed this is just for one single electron, then one has to integrate it over the distribution of the electron, assuming it to be a power law. Here we consider the power law to be 3 in our case. And when we integrate it, the fractional polarization, which is defined as the intensity of the light that is emitted in the polarized part to the total intensity, comes out to be like the simple formula. And for p is equal to 3 case, it says that the amount of linear polarization is around 75% of the total light intensity. So for this particular case, p is equal to 3, the total synchrotron intensity is, the expression goes like this, which depends on the magnetic field square and then the emission frequency given, which is here the spectral index is -1 for this particular value which I have considered in this model.
So I mean, I parallel is of course lesser than I perpendicular, right? So, but there is no acceleration along the field of that part, right?
No acceleration along the
field. That part cannot accelerate along the field, right? At a constant velocity.
Yeah.
So what then this intensity makes sense?
See, okay, just look at this plot. See, this is the dipole radiation, okay, which is happening in all directions. So in the cyclotron radiation case, if you observe along the parallel direction, there is an emission, which is the light is coming and that is circularly polarized. In synchrotron emission also will have some circular component in the perpendicular direction, but that component will be very small compared to this linearly polarized component. And that is only considered as a contamination. I mean, like that will contribute to the unpolarized part because there are different electrons, different orientations that are in this medium. So for the bunch of electrons, one can calculate this fractional polarization, which comes out to be like 75%. This is the intrinsic, degree of the polarization for the synchrotron emission. So generally, this is measured in the any polarized light is measured through something called the Stokes parameters. So any elliptically polarized light can be decomposed into the two linearly orthogonal polarized light with the relative phase between them. So this has like three unknowns: the intensity and then the relative phase, and this could be linked to the three parameters for the ellipse. That is, one of the parameters is the total intensity of this elliptical polarized light, and another is the chi, which gives the ratio of this semi-major and semi-minor axis, and psi is the orientation of the ellipse. And these two are linked through something called the Stokes parameter. So Stokes parameters are generally like I, Q, U, V. So I is the total intensity. Q is actually the difference between the intensity of the light in the two orthogonal directions. So U is also actually the difference between the light along orthogonal direction, but it is in a different angle that I'll show it in next slide. But this generally comes by taking the cross correlation of the Ex and Ey, and V will tell us the circular polarization component that is present in the light. So in general, this is the relation that is satisfied by this Stokes parameters. So this is strictly equality is strictly followed when the light is completely polarized. So if it is unpolarized, then the intensity will be more than the this one. So for the linear polarization, which is of interest to us, so the V is actually 0. The only relevant parameters are the Stokes Q and D parameter. So in the radio telescopes, they generally measure both Ex and Ey together using the dipole antennas, and then they are converted to the electrical signals, and later it are correlated with the other antenna signals. So here, I mean, this is how it is. This is the IAU convention that is normally followed in radio telescopes. That the Ex axis is the north and south axis, and the Ey is the east and south axis, east and west direction. So the Q, as I said, it's the difference of the two orthogonal intensities. U can also be written as difference between the two orthogonal intensity, but with an angle 45 degree making with the x-axis. The advantage of making this construction is that if there is any unpolarized component making contribution to the Ex and Ey, because of this subtraction, it will not appear in this parameter. It will only appear in the height. So here the fractional polarization could be defined as like this quantity is root of Q square plus Q square by. So this no, these are northeast. Earth axis northeast. No. This Earth northeast, north south is the Ex direction, and this is the Ui direction. This is the convention that is generally followed in the. It is an international convention actually. All radio telescopes follow. So this is, for example, the Hydra cluster, which has a central supermassive black hole, which is ejecting the jet, and the extent of the jet goes up to like hundreds of kiloparsecs. This is the radio image, which is at the frequency 2 gigahertz, and on the right hand side, what is shown is the fractional polarization plots. This is in the frequency range of 6 gigahertz to 12 gigahertz. All the intensities are clubbed together, and one can see that the fractional intensities of these clusters, for example, actually varies from somewhere from 0 to 6. It is not uniform. So there are two reasons to this why there is this fluctuation. One is that the magnetic fields which are causing this linear polarization is actually having a random structure in these clusters, which is associated with this gas. And also in the depth of the cluster, as the electrons are emitting synchrotron emission, the linear polarization, right? It is also getting fed when it is coming out. So when we are modeling, we have to take both of these facts into account. So in the simulation, what we do is we have a simulation cube, let's say like this. So we define something called the complex polarization, where the real part is the Q parameter and the imaginary part is V. The advantage of constructing this complex polarization is that both of the quantity Q and U could be handled together, because the property of complex number is that in the addition or subtraction, the real part and the imaginary part are handled separately. So this could be written in terms like this. So where psi is the intrinsic polarization angle, which actually depends on the magnetic field orientation, because whatever emission that is happening is actually perpendicular to the magnetic field direction. And also for this psi, we have to take into account the Faraday rotation that is happening. Let's say this medium is some patch is actually emitting the synchrotron radiation, and when it is passing through this medium, it is also Faraday rotating. So when I produce the 2D map of the system, both of this is taken into account. So I just integrate along the line of sight direction, and then divided by the total intensity to get the fractional polarization. So here I've shown the polarized emission for the fluctuation dynamo part, where this is the normalized QU, this is the fractional polarization. You can see that the fractional polarization actually varies from 2.7. There is nothing much we can see from this map, but if we plot its distribution, okay, we can see that the distribution is actually sort of symmetric with very less skew values. The average polarized intensity is around something like 0.35 for this case of a zero shear case. If we do the similar exercise for the case of the shear dynamo in the presence of shear, we first of all see that there is bright spot increases, more. The average sort of increases, and the distribution also sort of becomes very skewed. And even the Stokes Q, the average, like the normalized Stokes Q and parameter Q and U, both of them show the skewness in the distribution. So this is integrated along the Z direction. Let's say if I do it along Y direction and then the X direction, in both of this case, the skewness preserves. So what it is saying is that the distribution doesn't, the polarized intensity distribution doesn't depend on the direction in which we observe the Q. So it is sort of direction independent. So till now, the measuring the large scale motions in this cluster was very elusive from the observational point of view. So this kind of thing can be used as a diagnostic tool to identify the large scale motion in this cluster. The previous works were always done with the
So basically, observationally, you would expect to measure the polarization at what scales? I mean, what is your pinning of the structure?
No, this is okay. This structure extent is something like we are interested in, let's say 1 megaparsec or something. They're binned at around 1 kiloparsec.
So 1,000 pins.
1,000 pins or 500
pins.
Because the mean free path, if you look at of these electrons, they are around 0.5 kiloparsecs. 0.1 to 0.5 kiloparsecs. So one has to choose the your delta X, which is much larger than the mean free path in this system.
As you keep, I think what you've shown is as you keep increasing the shear, your system becomes asymmetric, but the smaller, well, it becomes it's skewed. It becomes skewed, but there's a double hump curve at the beginning.
This one or this one?
First and second.
So this is the Stokes Q and U parameter. See, this depends on the convention, but what is actually important is this fractional polarization is what measured. See. That's why I showed this cluster, where the fractional polarizations are generally computed. So initially, people were looking at the 300 megahertz or 1 gigahertz band. They were not able to identify because of this Faraday depolarization effect is coming from the start. So when they started looking at really high frequencies, like at 6 to more than 5 gigahertz, which is what Saranya also mentioned in his previous paper, that one has to look at the this field. These objects with higher frequency. So then one can see the sizable fractional polarizations without any effect of the Faraday depolarization. So yeah, so previous works were all related to just the zero shear case. So we had extended it to the shear case, and we see that there is a skewness in the distribution of the fractional polarization, which is sort of independent of the direction in which we see it. So this could be used as a really very strong diagnostic tool to sort of identify the large scale motions.
So this, excuse me, trying to piece together your thoughts. Obviously very useful. When you say this independent of the direction of observation, rather the direction of orientation of the clusters, okay, then we try, okay, so
see, for example, rotation measure I showed, it was a directional dependent quantity, because here, if you look at here, it was a directional dependent quantity. So it depended on which direction we actually make an approach.
Yeah, going back to your last plotted image, what I do see is that the regions of polarization tend to be changing, right? The extent of polarization now seems to almost seems to be almost you will act, but what do you actually measure? You measure the different fractional polarization.
a fractional polarization, this quantity.
You won't measure the Stokes parameters.
Stokes parameters are measured like this, Q and U, and then they compute the fractional polarization.
You can measure that.
This is like along the north-south axis, like Q plus is measured, perpendicular minus Q is
Yeah,
measured.
what I noticed was that it seems to be a little difficult, as you presumably keep increasing the shear, modulus, you keep increasing the shear.
I am not increasing, I am just showing the result for just a fixed shear case. Fixed shear case.
All right, but you still would know the dependence of the distribution of polarization upon the shear modulus.
From this plot,
Yes.
in a way,
So as you are increasing the shear modulus, the
skewness should increase.
yeah, the fraction of, rather I would say, if I look at the total fraction of polarization, it seems to be changing almost randomly throughout the very rapidly and random.
But if you look at the distribution, see there is structure present in this. One has to say one way of bringing out the structure is the distribution.
So basically, the upper one is a histogram.
Histogram.
Or,
Okay. Then one
size
can
of 1 kiloparsec to 1 kiloparsec.
then one can also look at the 2D Fourier transforms, which can also bring out the structures that are present here. One can also look at
Okay,
something.
so now this might be a simplistic question. How is the structure then correlated with the distribution of, you're looking at magnetic shift, how is it correlated with the distribution of outflows within the merging? Outflows or within the distribution of gases or with the distribution of
That we haven't done it. See,
no, but you could just be a direct extension of this. So if you've got a structure embedded within your simulated non-polarized emission, then assuming a certain shear modulus, there will be a certain correlation with the source of viscosity, which is either the gas outflows from the merging galaxies or what else would be. We think that the source of viscosity would be the gases.
viscosity meaning magnetic viscosity.
Well, right now I don't know which viscosity you've taken into account. Are you taking magnetic viscosity into account, or are you just taking the viscosity due to the flow, the gas flow?
Gas flow plus the resistivity, which is
What is resistivity?
no resistivity is the which is the inverse of the conductivity of the medium.
Okay.
Eta
So
parameter.
you're not accounting for the magnetic fields at all. So is that it?
No. See, if you look at these equations, here.
So you do have a field component, magnetic induction as well as the equation of fluid flow. That has a field inside of K cross.
Yeah.
Right?
Yeah.
So by looking at the distribution of polarization within a galaxy, like the image that you showed us, is it possible to correlate that with the anticipated field distribution or with the gas outflows? You're looking at galactic merger.
See, one thing.
Or you're looking at a cluster, sorry.
So the clusters of galaxies is similar. See, there is a motion in the gas which is sort of imprinting its signature on the magnetic field, and this magnetic field sort of leaving its signature on the polarization. So they are sort of connected in a way. So here I showed in these plots, for example, because of shear, there is a dy component has some structure that is getting developed, and this structure is causing the changes in the fractional polarization.
And how is the structure correlated with the distribution of gases in the cluster?
That one has to really look at, because see, nobody till now, when I was looking through the papers, for example, this work which came out just in September. So people actually plot the distribution for the rotation measure. They don't plot the distribution for the fractional polarization. This fractional polarization data has recently started coming out. And they just give the fractional polarization, that's it. They don't look at the distribution. If they start looking at like this, for example, what I've shown you, probably they'll see something which could, where then we can like sort of point out the things.
Can I ask another?
Yeah, sure.
So what was the value of the field? You had a range of fields, right? In the range of microgauss, but presumably ran this simulation for a range of values.
No, see, this is the idea of a dynamo, that there is a seed field that is there in the system, and then it grows to the equipartition strength.
So the equipartition field is of the order of 19,000.
It depends on, see, that's why this is, all of my plots are sort of scaled. You can scale it to the any system one is of interest. For example, I scale with respect to this quantity, the rho u square density. For example, here we scale to that. So whatever object of interest, so we need to particularly take those numbers into account and scale it to get those magnetic field values. Done. So this is the final conclusion summary. So we saw that the large scale shearing motions generally get set up in the margin activity of the clusters. So if you look at the root mean square value of the Rn in the non-shear case, no shear case, then it varies like 0.3 to 0.5. In the shear dynamo case, especially in the direction of the shear, the Rn had a really large value. We saw that this fractional polarization had a very skewed distribution because of the presence of the large scale motion, which could be used as a diagnostic tool to identify these motions in the system, which is still now remained elusive from the observation point of view.
Load simulation, do you make difference with this resistivity parallel to the field and perpendicular to the magnetic field?
No. It is considered isotropic. See, in the actual system, there is an anisotropy, okay? But here, because you will have an orientation of the, these particles which are creating this anisotropy in eta, they're oriented in all different directions. So they are sort of averaged in that sense.
But we have magnetic field. So in magnetic field, generally, we have parallel component or perpendicular component not very equal, right?
So magnetic fields could be different, but you're talking about resistivity of the medium, right?
Yeah.
That is considered to be isotropy.
Yeah, but the resistivity is coming, suppose, from the electron ion collision. So along the field, we will have different type of collision rate in compared to gyro frequency, and perpendicular to field we will have.
I agree. So let's say you have a difference along the magnetic field. You will also have somewhere the magnetic field which is perpendicular to that direction. So when you take the average, you get sort of an isotropic thing. That's what I'm trying to say.
So the first slide equations, going to solve the continuity equation.
No, because this is see, that's why rho is solved in pencil code. Continuity equation is solved in the pencil code. It is weakly compressible code. It is taken care into account, but because I already argued that in this clusters the turbulence is sort of subsonic, so this kind of a setup could be used.
So and these what are these two terms in this
This term.
Why that is
this total velocity we just substitute in these equations.
Right. So that has to come in the right hand side u, that is the u, right? Actually velocity.
No, see, this is total V, let's say. Then the V has two parts. One the shear and the turbulent motion. Then you'll get the four terms in it. Okay, one of the term cancels out because
whatever the u is there, it's a mean value and
divided.
So after the distribution, whatever you do, so because you are comparing the simulation with the actual things in the cluster matching. Okay, so what is the morphologically how they look like from your simulation?
See, this is just a simulation of a local patch. Okay, it is not a global simulation. So our motivation was to understand what the large scale motions, what signatures it will have it on the observers. So for that one has to run actually the global simulation
And I am also wondering because you are looking at the dynamo growth with the increase of this velocity, sharing, share that.
No, see, shear is constant. This is increasing because of this x value. X is increasing, so this.
So in the situation, you share and without share, and there are some numbers, maybe in there something. So in that case, don't you measure this? What is that electricity and some kind of LCD also magnetic density? How they are going to get?
So because it was not of interest to us, we didn't measure it. But of course, one can measure it. But here the fluid velocity is the net fluid velocity is 0 because we are forcing it non-helical. But the magnetic field, of course, can get the helicity. Generally, it is seen that the total magnetic helicity in the non-helical flows are 0. But at the larger scale, magnetic field have one sign of the helicity. At the lower scale of the magnetic field, it will have the opposite sign of the helicity. So that the total, when you add it up, it will be like 0.
Something interesting, non-helical case also, the magnetic field will generate the locals. This is the important thing in this study.
See, you will always have a fluctuation dynamo. No matter, see, all that you require for the dynamo to happen is that you need vorticity, that's it. The presence of vorticity, that's it. So that will give you fluctuation dynamo whose scales are generally, that's why I showed you its integral scales. The scale of the magnetic fields are small compared to the velocity integral scales. But to get the mean magnetic field whose integral scales are larger than this velocity integral scales, then one has to inject the helicity in the system. That is what happens in some
So that is large scale.
That is a large scale dynamo. So the small scale dynamos are very robust dynamo. All that counts is that you have to, the resistivity should be below certain threshold values. Then it can just trigger that. In turbulence, you are always expected the vorticity motions.
Sorry, so in small scale, we don't find helicity.
Yeah, no. Net helicity is 0, but at the point if you go, there could be fluctuations. There could be fluctuations.
So, yeah, you said the small scale dynamo is always happening.
Yeah.
But that is because you have a Prandtl number sufficiently high.
Now, people have shown, for example, Alexander Shekochin and all, where they have looked at for the Prandtl number less than 1. So in 2003, 2004 paper, they have shown the dynamo for low Prandtl number cases.
So the solar case people have done simulations with small Prandtl. Only at high Prandtl number it happens.
No, low Prandtl number also they have shown. I know the case for 0.5, 0.1 Prandtl number, they have shown the dynamo.
That is not so small. Generally, on the sun, it's believed to be 10 to minus 3 or 4.
Okay, there I don't know, but it has been shown for 0.5, 0.1. Chekoskin leads in explanation.
Galaxy scale, we seem to be having always
Yeah. Galaxy clusters.
because viscosity is high.
Viscosity is high because the temperatures are higher. The temperatures are higher, so it makes the collisions more probable, so viscosity increases. But because the temperatures are higher, it also increases the ion conductivity, which sort of decreases the resistivity.
There are no more clouds.
No more. Very interesting. Thank you.
Yeah, good. Good.
Yeah.
Very good. Can you merge two stars since we're telling galaxy merging is happening? Can you simulate if I tell you two certain stars? Can you merge and tell me what is the outcome?
I don't know what kind of a code I have to use for that.
I don't know. I want to merge two things. I can tell why I am interested.
Okay.
I want to see the outcome.
It generally happens in globular clusters kind of a system, no? Because in galaxies it don't happen because these physical distances are really large.
No, since you told galaxies are merging, stars also merge.
Yes.
So what I'm telling is, do you have some tools which can simulate two stars merging? And then what will be the resultant evolution of such a merged product?
You have to think.
Okay, we will discuss about it. Yeah?
You
Okay.
have to think
So,
which star is it.
One question.
Ah,
When you
something like that.
substitute this velocity there, like what kind of time and spatial dependence you have on this velocity? Like, is there any higher order term which you neglect, or it is like
No,
constant?
nothing. This is no approximation, this is simulation. We are solving.
No. When you have a velocity like this one,
Ah.
this is what kind? Yes, is just a constant, is it?
Yes, it's just a
Not a
constant.
function of time or.
See, at the local, see, this is a differential velocity,
Hmm.
differentially rotating system,
Hmm.
right? So it has a variation across R. But at the local patch, if you go there, then it seems like this.
Yeah, but I mean, what exactly is this? Yes, like how do you like? Is it like parameterized or
It is parameter, basically it is,
spatially dependent or?
yes, see, you know, in the galaxy, it is more R times B omega,
Okay.
which is a function of R.
Hmm.
Because this goes like, you know, R to the power of minus.
Okay, but yeah, so when you substitute there are these cross terms, everything you take into account, is it?
Yeah.
There is nothing like
No,
you
but-
don't ignore any higher order.
Nothing.
And
This is
time dependence, is there any time dependence?
of the S. No, these are a steady state system, no?
Okay.
Once it is like rotating, the S is sort of fixed. But in a galaxy merger, it could be time dependent. It could be time dependent. See, if you try to put in everything, then
Yeah, because when, I mean, this is completely different things like we do, but still there are, when